This is part E. What we're going to do is compare these two functions and then compare their derivatives. We need to first of all realize that g of x is function f of x with a vertical translation up 6 units. So let's just see. If we have, let's call this f of x. G of x then would be the same function but up here. And if we take a derivative, ugly functions I realize, but if we take a derivative at this point, we'll call this c. And I come up here and do the exact same point, then the derivative of the function f is the slope of the tangent at c, would have exactly the same value as the derivative of g of x at the same point because the two lines are parallel. Okay, so let's go on to our next problem. Here we're looking at function f of x equals cosine x on the interval 0 to pi divided by 3. Find the average rate of change. Average rate of change. And we're going to be comparing that later on with instantaneous rate of change. So let's just review average rate of change. Average rate of change is the same thing as the slope of a secant. Now the slope of a secant is nothing more than our slope formula. So we'd have f of x plus delta x minus f of x divided by delta x. So if we're going to look at this, let's just go to the inspires. I'm going to insert a new problem, and so we can get to F1 again. And let's see, we're going to have cosine x as our function. I'm going to change the window setting a little bit. I'm going to make this negative pi divided by 2, and I'm going to make this then pi, and we'll tab it, the scale, let's say every 1 unit. The range of the cosine would go from -1, and I'm going to make this top maximum to be 1.5. and I'm going to scale by 1. So I'm going to use that kind of a window. You can use whichever you choose. That's the one I'm going to use though. Okay, we need to put some points on here. And so be careful. Don't try to place it right at 0. Again, as we know, sometimes the Inspire thinks it's at a point and it's not. So it's best if you just go ahead and change those coordinates so that we know we are so specifically at the point we want. Don't try to use a decimal for this pi divided by 3. We can use pi divided by 3, and we have our points there. Again, we're looking at the average rate of change, which means a secant, so I'm going to go through and do that part also. And we have then our secant line segment, but we're going to use the line so we can do some calculations on it. When we talk about average rate of change, we're talking about the slope of the secant. So let's just go ahead and get our answer ahead of time, so that we know, we'll know if we're close to that when we actually compute, use our analytical. And I'm going to go through and label this as slope of secant so we don't forget what that refers to. Okay, so we know the answer, but let's do this analytically. What we need to do to find the slope of the secant then is to take cosine of pi divided by 3 minus cosine of 0 divided by pi divided by 3 minus 0. Let's look at this first and see what we can come up with. First of all, pi divided by 3, we're going to build our proportion here. So the radians of the angle is to the radians of the entire circle, as the degrees of the angle are to the degrees of the entire circle. And so we come up with, trust that you'll pause and do this for yourself if you're not sure of it. But just solve for D and you'll find that D is equal to 60 degrees. Then, in order to determine what's the cosine of that, I always build myself, or at least have it in my head, that I have a 30, 60, 90. You've seen me do this in class. And reflect it, so I have two of them, and that creates an equilateral. So if this side of my original is 1, and I just replicated that over, that whole side is 2. Even though it doesn't look like it, this would then be equilateral, so that'd be 2, and this side is 3. So the cosine of pi divided by 3, cosine of 60 degrees, is going to be 1/2 minus, now the cosine of 0, I'm going to go back to my unit circle, and remembering that every point on the unit circle is also cosine sine, as well as xy. And at 0 degrees, I have 1, 0, so this would be cosine of 0 is 1, and of course this is pi divided by 3. So if I take a look at that, I have negative 1/2, and I'm going to now multiply by the reciprocal, so 3 divided by pi. So the slope of the secant is negative 3 divided by 2 pi. Now that's not what the Inspire showed. It showed negative 0.477. So we need to know, is this equivalent to that? Now this is my exact answer. So what is my approximate? So let's go over here. Let's add a calculator page. And let's just build a fraction. Let's see, we had 3 divided by negative 2 times pi. And we're going to have to do, of course, Control Enter. And sure enough, it is equivalent to that. So we did do our work correctly. And what we need to think about is, what does this represent? Let's go back to our graph. The slope says that for every 1 unit increase in input, our output is changing approximately by negative 0.477 units. So for every 1 unit increase in our angle, the ratio between our adjacent and hypotenuse sides is decreasing approximately negative 0.477 units. Now the second question is, what's the comparison between that and instantaneous rate of change? An instantaneous rate of change is the slope of the tangent. Now we're not going to use the limit definition. That was in section 3.1. But we do need to find out what is the derivative of cosine. So we need to look at what is our derivative of cosine, and if you go back a few pages here, we see that the derivative of cosine is opposite of sine. So that will be what we're going to use here. And we're going to, again, this is the derivative, and so this is going to be the opposite of sine. It says at the endpoints, so we're going to want to determine the derivative at 0, and then the derivative at pi divided by 3. Well, if we look at the derivative at 0, we have the sign, opposite the sign of 0. Go back to our unit circle. At 0 degrees, sine is 0, so this is just 0. The derivative at pi divided by 3, this would be the opposite of the sine of pi divided by 3. And if we go back to our triangle here, the sine is the opposite divided by hypotenuse, so that would be the opposite of the square root of 3 divided by 2. Again, let's find an approximate value for that, and it turns out to be negative 0.8 0.66. Now, what is our comparison with these? Well, on our inspires, if we look at this and we draw a tangent at each of our endpoints, let me go back and make sure that we have that. A tangent there. We have a tangent there. That's a horizontal line. Is it consistent with thinking that the slope is 0? The answer is yes. And over here then we would have one that is steeper. This tangent is steeper than the secant, so its slope should be more negative than that, which is true. Instantaneously at this point, for every 1 unit increase in input, our outputs are changing by approximately decreasing 0.866 units. Okay. We can verify that, of course, by looking at the slopes of these, and so the slope of that would be, of course, negative 8.66. This, in fact, is horizontal, which gives us that value. Okay, so to wrap this problem up then, we have that negative 0.866 is less than negative 0.477 is less than 0. This is your average rate of change that we have in there. Okay, we're going to move on to the next problem and talk about rates of change. And our rates of change are one variable with respect to another. Let's just kind of identify it's the rate of change of the output with respect to the input variable. Our position function, the function s, gives the position, so the output of that is position. So the output of the position function is the position relative to the origin of an object as a function of time. And so time is our input. We also then have that over a period of time, which will be defined as delta x, the object changes its position by an amount of, and so we would have s of t divided by, or excuse me, s of t plus delta t minus s of t. This again is input, delta t is input, and this would then be an output. Okay, if we're looking at rate, you know distance is rate times time. If we divide both sides by time, we have rate is distance divided by time. Average velocity is change in distance divided by change in time. Delta s divided by delta t. So delta s again is change of s position of t plus delta t minus s of t. This is our output divided by t. Okay,